Welcome to this session on Mathematics, Chapter 2 Polynomials for Class 10 or Grade 10. We are covering Section 2.2 Geometrical Meaning of the Zeros of a Polynomial, and in this session we are talking about graphs of polynomials. So we are trying to find out how do graphs of polynomials look like, and let's begin with the constant functions and the linear polynomials, and we will try to see how do their graphs look like. Our first example is px is equal to 4. It is a polynomial which is a constant function. That is, value of this function will remain same for all the values of x. So let's say x becomes 1, it will give us the value of polynomial as 4. When x becomes 4, again the polynomial value will remain 4. That is, the polynomial is a constant function. The other example that we are taking right now is px is equal to 2x plus 2. This is example of a linear function. It's called linear function or a linear polynomial because the maximum power of variable x in this case, it is 1. So it's a linear function. So now we are trying to see how do the graphs of these two types of functions or polynomials look like. So here it is. The plot or the graph of px is equal to 4 is plotted in this diagram, and we see that this is a horizontal straight line which cuts the y-axis on a point 4. So when y is equal to 4, this is the intersection which is happening, and it's a horizontal line. Similarly, the plot of 2x plus 2 is a straight line, but it's not a horizontal line. This line has its slope and it intersects the x-axis at a point. Here in this case it is -1. So we can say that the graphs of linear and the constant functions are straight lines. So now let's try to see how do the graphs of quadratic functions or quadratic polynomials which have degree of 2, how do they look like? So we are trying to find out the graphs of, let's take examples of px is equal to x square, px is equal to 2x square, or px is equal to 4x square. So we are now trying to see the graphs of quadratic functions and see how do they look like. So here is our normal x-axis and y-axis. We plot px is equal to x square and we get a parabolic shape. So this parabola is kind of you can say opening upwards, so it is open upwards. Now let's plot px is equal to 2x square, and this is another parabola which is little bit inside the previous parabola. And then let's plot px is equal to 4x square, which is another parabola opening upwards and it is inside. So we see that as the coefficient of x square, we see as we are changing it or as we are increasing it, the graph is stretching vertically. So from x square, when the coefficient is increased to 2x2, from here the coefficient is 1 and here the coefficient is 2. So when we move from 1 to 2, the graph is moving inwards or is stretching along the y-axis. And then when we move the coefficient or when we make the coefficient from 2 to 4, the graph or the parabola is compressed, you can say, or is moving or is stretching more vertically along the y-axis. So but what happens when the coefficient of x square is negative? Because in all these three examples we have considered the coefficient to be positive. So here it is +1, here it is +2, here it is +4. But what happens when the coefficient of x square is negative? So let's see how do the graphs look like when the x square coefficient is negative. So for that case, let's say we are taking examples px is equal to -x square, px is equal to -2x square, and px is equal to -4x square. And in these cases, the values of px becomes negative, and all the graphs will become reflected along the x-axis. That is, they will become mirror image of the graph as if the coefficients were positive. So let's first draw and then we'll talk about it a bit more. So this is our x-axis and the y-axis. We have taken them two of such pairs, and let's plot p is equal to x square, and let's also plot p is equal to -x square. So here you see, as we were talking about, along the x-axis, that is along this x-axis, we see that the two polynomial, so the two functions are mirror images of each other. Now let's plot px is equal to 2x square, and let's also plot px is equal to minus 2x square. Let's also plot px is equal to 4x square. This is our third function here, and we also plot px is equal to minus 4x square. So we see that when the coefficient of x square becomes negative, the graph is becoming like a mirror image, or is getting reflected along the x-axis. So if to just remove the lines here, and let's see how does this look like. If you were to use the same pair of x-axis and y-axis, you can see that they look like images of each other, and along the x-axis, if you were to put that like kind of a mirror, you will see as if these things are getting reflected. So graph, when the coefficient of x square is negative, the graph becomes reflected along the x-axis. So now let's take the next case and see, instead of varying the coefficient of x square, why don't we vary the coefficient of x? So let's see what happens when we vary the coefficient of x instead of coefficient of x square. And we will do that by first taking examples. Let's take example functions as x square plus x. Another example we have x square plus 2x. Another we have is x square plus 4x. You will notice that here the coefficient of x is changing. First of all it is 1, then the coefficient of x is 2, and then the coefficient of x is 4. So this is our axes, x-axis and y-axis. Let's plot the first function x square plus x, and this is not to scale, but more or less this will look like the shape that is shown here. Now let's plot px is equal to x square plus 2x, and then let's plot the third function x square plus 4x. So we see that as we are increasing the coefficient of x from x to 2x, or meaning coefficient is changing from 1 to 2 and then from 2 to 4, the parabola or the graph is shifting left. So graph is moving towards left, and it is also moving down a little bit. So we can say that as we increase the positive coefficient of x in a polynomial, the polynomial's graph moves downward and to the left. So let's see, if you see from green then brown to blue, the graph is moving left and it is also moving down a little bit. So now let's consider what happens when the coefficient of x is becoming negative and we increase it. So here the coefficient, so far we have talked about the coefficient of x being positive, but now we shall talk about the coefficient of x being negative, and we increase it. Again, we will take some examples. First example is px is equal to x square minus x. Then we have x square minus 2x. Then we have x square minus 4x. So here you will see that the negative value, or the absolute value of the negative coefficient, is increasing from minus 1, then it is becoming minus 2, and then it is becoming minus 4. And here is our axes, y-axis and x-axis. And the first, let's plot x square minus x, which is a small parabola here, and then let's plot x square minus 2x, and then we have our third plot x square minus 4x. So here we see that as the absolute value of the negative coefficient is increasing, the graph is moving rightwards and it is also moving a bit downwards. So you see green is becoming brown, and then the brown is becoming blue here. So we can say that as we increase the negative coefficient of x, and we are increasing it in the absolute value in a polynomial, then the polynomial's graph moves down and to the right. Here if you see, the graph is moved to the right and it is also moved a little bit down. So now we shall start talking about next case, that is what happens when we vary the constant term in our polynomial. So if you see here, we have x square and we have x, but we do not have any constant value here. So let's now talk about that scenario. And we shall start that discussion of a quadratic function having x square, x, and the constant term. So let's take the examples. The first example is x square plus x plus 0. Our constant here is 0. The other example is x squared plus x plus 1. So the constant term here is 1. And another example is x squared plus x plus 5. And the constant term here is 5. X squared plus x and minus 5. So the constant term here is minus 5. So you see here that we have not changed the values or the terms in x squared and x, but we are varying the constant term in the different polynomials. And now let's see how do their graphs look like. So if we plot them on our usual x-axis and y-axis, these four functions will look like this. So the graph of x squared plus x plus 0 is plotted right here. Then x squared plus x plus 1 is plotted here, and x squared plus x plus 5 is plotted here, and the last function is plotted in here. And you will notice that as we vary the constant term in the polynomial graphs moves upward or downwards. So if you see from here, let's say we had 0 and then we had 1. So from 0 term here to 1, the graph has actually moved upwards. So like this. And also we note that the value of the constant term is the point at which the graph intersects the y-axis. So if you take, for example, let's say this polynomial x squared plus x plus 0, and this is plotted here, and this plot is intersecting the y-axis at 0. And now let's take the plot of x squared plus x plus 1, which is plotted here, and it is intersecting the y-axis at the value 1. So you will notice that the constant term here, it is 1, and the intersection of the graph is happening at the value 1. Here in this example, x squared plus x plus 0, the constant term is 0, so the intersection is also happening at the value 0. And let's say here in this example, px is equal to x squared plus x minus 5. The graph is plotted here, and this graph intersects the y-axis at the value minus 5, which is same as the constant terms value. So we can say that, I will repeat here, that as we vary the constant term in a polynomial, the polynomial's graph moves up or down vertically, and the value of the constant term is the point at which the graph intersects the y-axis. Now also we have seen that how do the graphs of different polynomials look like. We have seen the quadratic polynomials, constant functions, and the linear polynomials or linear functions. Now let's talk briefly about the turning points in the polynomials. And generally speaking, a polynomial of degree n can have up to n minus 1 turning points. So if a polynomial has degree 4, it can have up to 4 minus 1, that is 3 turning points. But what are those turning points? A turning point of a function is the point where the graph of the function changes the direction of the slope. So if the slope were downwards, then turning point is the point where the slope starts becoming upwards, or vice versa. Vice versa means that the slope might be turning upwards, and then when the turning point comes, the slope becomes or turns downwards. And in other words, we can say that the gradient of the function changes from negative to positive or positive to negative. And now let's talk about some shapes or some turning points in different types of functions. So a quadratic function has a degree of 2, and therefore, as we just talked about here, that the maximum number of turning points it can have is 2 minus 1, that is 1. And that indeed is the case, because a quadratic function's graph generally looks like this parabola, and here is the turning point here, where the slope is coming first of all downwards, and then after the turning point it goes upwards. Similarly, the cubic functions, these are the functions which have degree 3. So at the most they can have 3 minus 1, that is up to 2 turning points. Any given graph can have less than 2 also, but the maximum number of turning points in a cubic function's graph will be only 2. And here are the examples. We have this plot, and the turning point number 1 is here, turning point number 2 is here, and then similarly another plot we see here which is having only one turning point right here. Now next let's consider quartic functions which have degree 4, and we know that at the most they can have 3 turning points, and here is the example of our quartic function. It has 1 turning point, 2 turning points, and 3 turning points. So turning point, and this is the maximum number of turning points that we can have in a quartic function.